Okay, next lecture on radiation concerning few factors. That's again Reinhold Kneer speaking here, and let's have a look at today's learning goals. First, I would like to introduce the principle of few factors to let you understand the difference between what is being radiated by a surface compared to incident radiation, and it's mentioning here radiated and not emitted, and we shall see the difference. Then we talk about diffuse radiation as 3D space, and then make this a little bit more concrete by looking at radiation. Sorry, I need this here, the laser point, radiation from one surface that hits another surface. We do that for very small ones and then go to the more general case of larger surfaces. But let's now start here. The principle of few factors. If I look at this body 1, and each point at this body is supposed to send out diffuse radiation. Diffuse means there is no angular or spatial preference. So into all spatial directions there's the same amount of radiation emitted. And we just look at 3 points at the surface. And of course the entire surface is radiating, but we just use 3 points here for the as example. Now this hits another object, body 2, and we just look at these 3 points, and of course then we can try to calculate which fraction of the radiation emitted by body 1 really hits body 2, and the rest just goes somewhere else. And in order to do so, we look at here from this point at a semicircle which contains all the radiation emitted from that point, and a certain fraction hits that body, and we can capture that by the partial region or the angle beta. So the fraction here is then beta divided by the half circle, semicircle by pi. Now we have to do this for any point on the surface, then we have to integrate on the surface of body 1. Excuse me. Now if we generalize this for a 3D space, well, we need to take into account the orientation, the distance, and so on. In order to do so, I bring here now another geometrical arrangement. This geometrical arrangement is shown here. There's a, let me pick another, not the laser pointer, but a pen. Sorry. We have a little area. Oh, this straight line is an artifact, sorry. Now let's go to the laser pointer again. This area is radiating. You can imagine if this was like a little insect, a spider, whatever, that you put your cup of coffee over to put a trap. So here we are putting a trap by a semicircle and or a semi-sphere. So all the radiation that is going out from D capital A hits the surface of that sphere. And now on the sphere we define another surface and look at the radiation that comes from this D capital A to that D small a, and there is a dx that we can define with the use of the various angles. Here you see a phi, and here you see a psi, or the angle psi, that's d psi, that's d phi. So dx is defined, there's the radius, as r times sinus of phi times d psi. dy is defined as r d phi. So this gives us the surface of this small element on the sphere surface. And now we want to estimate how much radiation goes into this direction, or calculate. So there's a solid angle d capital omega that depends on phi and psi, and this is the surface of this element divided by the radius squared. So this is dx times dy, r sinus phi, d psi, r d phi. And this can now be put into an equation, and you see here dq dot from capital A to small a surface increment is L, I will explain what L is, times the omega times the A times cosine phi. So this is the projection of the radiating surface into the viewing direction. The solid angle is defined as above, that's the surface here divided by r squared, and this here is radiance. Actually, this equation is the definition equation for radiance. If I put this on the other side, then it reads L is the amount of energy or heat flow rate that comes from that surface divided by the projected area times solid angle. So in more common words, it's the power of the radiator divided by project area and solid angle. That's this radiance L. We are not using this property further on, it's just here in this context, so you that's where we will have this here. Now let's move on. The integration by doing separation of variables, we bring dA on this side, we have then dq dot over dA is then the integral L times cosine phi times the omega. We continue and assume that it's diffuse. This means the radiance does not depend on phi and psi, so it can be pulled in front of the integral. And at the end, the dq dot over dA gives small q dot 2 primes, and as it's integrated over the hemisphere, I give it here the index hemispherical. That's L, which is put in front of this one here, and we have a double integral because the omega brings the d psi in. So it's and the angles are running, psi is running all around and phi is running here from bottom to top. So from 0 to pi half, from 0 to 2 pi. Now if we solve this one here, so we have still q dot 2 primes hemispherical is L times this double integral, and now let's just take the pen again. So this one is here. So we solve first the inner integral, that gives us 1/2. And go back to the laser pointer, and then putting this in and doing the outer integration gives us pi. So at the end is q dot 2 primes hemispherical, that's pi times L. And we did that because we could do that because we assumed diffuse radiation. Or in other words, L becomes q dot 2 primes divided by pi. And we shall see later on that q dot 2 primes times area will be given the name surface brightness. I will get back to that just to mention it here. So I write it down. Surface brightness. We will come back to that in the next video. So let's now move on and do radiation transfer between two surfaces. We start with the increment dA1 and want to understand how much radiation is going to hit the little increment dA2. So dA1 is radiating everywhere, but we're just interested into this direction R. So how much goes there? So this is dq dot from 1 to 2. That's L1 cosine phi dA1 d omega, the infinite solid angle. Cosine phi 1 dA1 is the projection of dA1 into direction R. The d omega is the surface here, the projection into this direction divided by r squared. Now L1 we calculated before, that's q dot 1 2 primes over pi. Now we can put that together. Putting L1 in here, we can put it in front of the integral because we still assume that it's diffuse. We have the 2 cosine from the projection of dA1 and dA2 and r squared. And as I said, because of diffuse that's in front of the integral. And we can formulate the same for the radiation that goes from 2 to 1. Then we have q dot 2 primes over pi. But this expression behind these two integral expressions are identical. So the geometrical components here are identical. And we shall see that we can make use of that later on. Now, if we look at the radiation that goes from A1 to A2, we are doing the integration. And now I'm bringing here the definition of a few factor. For the few factor, we use the symbol phi, capital Phi, and two indices. The first index is the emitting surface or the sending out surface, and 2 is the receiving surface. And this is radiation sent from 1 in direction 2. And it's divided by the total radiation that is being emitted from 1. So it's q dot 1 to 2 divided by q dot 1 2 primes A1. Now I can this one take from here and put it in there. So I get phi 1 2, that's note I have here q dot 1 2 primes, q dot 1 2 primes, that cancels out. The A1 stays there and the pi is pulled into the integral. So this is my expression for phi 1 2. And if I make now, let me go back. So I have here my phi 1 2, and now I will go back to this geometrical expressions being the same, and this means I can put this on the other side. These two are the same, so q dot 1 to 2 divided by q dot 2 to 1, that's q dot 1 2 primes divided by q dot 2 primes. I use then the definition for the few factor and can come up by equating this to phi 1 2 times A1 equals phi 2 1 times A2, and the intermediate shows you how this equation has been generated. So there's kind of the symmetry which is called reciprocal rule, and often we will use that if we know phi 2 1 but don't know this one here. We bring the area on the other side and calculate phi 1 2. Now let me use the laser pointer again. The few factors of some systems are put in the appendix of our lecture notes. You see here phi 1 2 for this arrangement. That's kind of a wall and an attached floor, or like a cutaway shoebox. So, and the dimensions are, this extension is x, this is z, that's y. And you see here curves y over x, and here is c over x. To make this a little bit easier, if y is very large, then the radiation will go quite somewhere. So this means if y over x has a large value, the few factor is pretty small, because most of the radiation from A1 goes to another direction than to 2. However, if I would increase the surface of A2, means if I increase z, then I see that the few factors are getting larger in this direction. So that's how you can interpret that. And another diagram is, for example, this is now the shoebox, and it's the bottom and the ceiling. And of course, if D was very small, almost all radiation from A1 would reach A2. So D being very small is being in this corner and is in that corner, and then we reach almost the few factor of 1. Or in other words, if the distance increases, my few factors go down, and distance increases as well, so I'm here in the lower end if D gets larger and larger. We will train also how to calculate these few factors. These diagrams are just meant as an help, so that you don't have always to calculate the few factors mathematically. It's just a geometrical exercise to calculate few factors for real configurations, and we will provide you with examples and problems there. The comprehension questions at the end are which parameter of radiation that is emerging from a surface are described by the View factor concept. And you will have to train to calculate radiation exchange by using the View factors. And the question is, what if these bodies radiate directionally? We just looked at it in a diffuse manner, so direction did not play a role. So give it a thought, what happens if it's directionally? And the next point would be on what parameters are the View factors depending on. Thanks for listening.